Hi, my name is Charan Rai and I will be discussing about neural networks in this lecture. First of all, let's briefly discuss about the overview of the lecture. So, first we will be discussing about the introduction of neural network, and later we will be talking about McCulloch-Pitts neuron. Then we will understand what is decision boundary and some examples using MP neurons on Boolean functions. Later, we will be discussing about perceptron. This is very important. Then we'll understand what is weight vectors. We'll then talk about learning rate. Later, we'll be talking about network of perceptron. This is single perceptron. We'll be talking about a network of perceptron that is actually neural network. A network comes from here, and we'll solve a XOR gate problem using neural network. We'll talk about loss function and sigmoid activation function. What is that? If anything doesn't make sense right now, stay with me. We'll have deeper understanding. So what is neural network? As we can see, we have some input and this circle is has G and F and output. How this mean? So we may know about the neurons. Let's say this is a neuron. This is how a neuron looks. This is the analogy that is taken um, to give the name the neural network. So this is axon, this is dendrons. So input, first of all we have some input and this dendrons get input and this axon, after that they output, and later we will have another neuron, and this is a interconnected chain of neurons. So this is how actually our neural network work. There will be some input and a function that will be calculated on the input, and we will get the output from a single neuron, and we will add multiple neurons in this neural network. So what this G is called? G is called aggregate input, and F is called activation. So G combines all the inputs. If it is one input or multiple input like x1, x2, so G combines all the input, and F is a function that maps G to the output. So in this MP neuron, sorry. So in this MP neuron, we have so many inputs. Let's say x1, x2, dot 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 up to xn. So we can see G as the summation of x1, x2 up to some dimension xd, and F is such that whenever the summation of x, that is G of x, is equals to, this function is greater than equals to some cut of theta, we call it as y equals to 1. So output is 1. So whenever G is the summation of x is less than some cutoff, we call it y equals to 0. The output of this neural network is 0. So first we calculate G, second we calculate F to get to map the G into output. Let's talk about decision boundary. So let's say you have positive um, samples here you have negative samples here. So basically a decision boundary is a boundary that separates your positive with your negative. This line is called decision boundary. So here your x2, here is a feature x1. So whatever is up here, that will be greater than equals to the cutoff theta, and whatever is down here, that will be less than theta. So MP neuron basically can do separate this linearly, this is a very important, linearly separable data. Let's see one example. Let's add a blank page. Okay, so you have a cutoff, let's say theta equals to 1. So here in this axis you will have 1, here you will have 1, and this will be the decision boundary based on theta equals to 1. And if you increase the cutoff, let's say theta equals to 2, the decision boundary will be like this, where x1 here equals will be 2, x2 here equals to will be 2, and whatever up here will be considered output as 1, and whatever is down here will be considered at output 0. So same goes here. Now if we try to calculate AND gate, this is most basic Boolean function AND gate based on this MP neuron. So this is our axis here, then we have, okay, let's draw it little. So this is our axis, let's say x2, x1. So we have 1 here, we have 0 here, we have 1 here, and we have 1 1 1. So let's write some color. So this is our positive output, and all these are negative one. This corresponds to 0 0 0. This is 0, this is 0, this is 0. So how the decision boundary will come? The decision boundary will come somewhere like this. So using this boundary we can separate, and we can compute AND gate. Whatever is up here will be y equals to 1, whatever is down here will be y equals to 0. Here will be 2 1 2 1 0. So this is how we can do AND gate using MP neuron. So if we want to do OR gate using MP neuron, what we can do is at 0 0 we have 0, at 0 1 we have 1, at 1 0 we have 1, and 1 1 we have 1. So if we want to separate this using MP neuron, we can draw a decision boundary here. So whatever is up here will be given as y equals to 1, and whatever is down here will be given as y equals to 0. So we have to choose theta such that the decision boundary lies in the middle of these two type of output. So if we want to do NAND gate based on this MP neuron, what we can do that this, let's say this is our axis, this is all similar. So wherever y equals to 0 0 there will be 1, wherever it is 0 1 we will have 1, 1 0 1, and 1 1, that will be 0. So red says it is y equals to 0. So in this case, we will draw a decision boundary like this, and we will choose theta such that the positive result come underside of this decision boundary. So here the y equals to 1 will be in that side and y equals to 0 will be this side. So if we solve a equation based on this decision boundary, we get so if we solve this, we can if we try to solve this, we can solve this with this MP neuron. And for the NAND gate, let's say this is our axis x1, x2. We have 0 0 1 1 0, that is 0. This one is 0, this one is also 0. So yeah, as we can see, this is linearly separable data. We can separate with this decision boundary. Above this, we can say y equals to 0. Below this, we can say y equals to 1. And we can take theta such that whatever the summation of x1 plus x2 comes greater than equals to theta, theta will be negative here. So we will get y equals to 0 and x1 plus x2 is less than theta. Sorry, this thing will be greater than equals to theta. This thing will be less than theta. We have positive result here. So negative result here. So theta will be some negative number here, and here theta will be some theta will be some negative number. If we sum this 0, we will get y equals to 1. So the problem comes in the XOR gate. So let's see, this is x1, this is x2. So 0 0, this is 0. The 1 0 1, this is 1. 1 0, this is 0 1, and 0 0, this is, so you cannot put any decision boundary to divide this red with this green one. So this is not linearly separable. This is not linearly separable. So we cannot differentiate between these two using a single line. So that's where this MP neuron fails. So MP neuron is basically a decision boundary 45-degree tilted here. So this will always be following like this. So it cannot rotate also. So to give it a chance of rotation, we introduce this perceptron neural network. So here we will have x1, x2, x3, dot 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 xt, some dimensional data, and we will define such that every input multiplied with this some weight vector multiplied with this weights. So what we can say that f equals to, first define the g, okay. So w1 x1 w2 sorry w2 x2 plus up to wd xt. Fine. So we can say that summation of wi xi, whenever it is greater than equals to theta, we will say y equals to 1, and whenever wi xi is less than theta, we will say y equals to 0. Fine. So this is how a perceptron works. It introduces some weights so that we can tilt the decision boundary according to our needs. So if we replace, let's say we have a constant here also, that will be w0. So we can say that, sorry, let's say, yeah, this theta, okay. So f equals to summation over wi xi greater than equals to theta. If we take theta into this side, we can say theta is w0. So w0 plus w1 x1 and so on. So this is our new activation function. F looks like w0. So here we can introduce one another constant, that will be x0. So x0 is nothing but 1 and w0 is nothing but the previous theta that we were talking about, that comes this side, so this will be negative. So using this perceptron neural network, we can separate linearly separable data. So how can we do that? It's basically the same. So here we will take w1 w2 as 1 and we can convert it to MP neuron, and we can solve all the basic booleans that we have done previously. So one important takeaway is that perceptron can always separate linearly separable data. Now we will talk about more about the decision boundary. So let's say this is the boundary we used to get. This axis is x2, x1. So this direction will be the w1, w2 vector. So that will always be perpendicular to, let's say this is our data point 1, this is our data point 2. So 1 to 2 the vector is like this, and the decision boundary vector w will be always perpendicular. So we get this straight line. Straight line has a norm that will be w1 w2, this vector, and it will always be perpendicular to the decision boundary. So we can see that our f was w1 x1 w2 x2 plus a w0, that is 0. This is our converted x was looking like. So we can rewrite this as w0 w1 w2. This is a row vector, and we can multiply this one with this vector. This is our input vector, this is our weight vector. So if we multiply this, we get 0. So we can say that all the w1 w2 w0, all the weight vector is perpendicular to the input vector. So input vector lies in this direction and weight vector lies in this direction, and there always be a 90-degree angle. This is the interpretation of decision boundary. Let's move on. So let's say we have a data that is like this. We have a data that is like this. We have some positive inputs here, we have some negative here, and one negative is like here, and our initial weight vector was like this, so that our decision boundary was like this. Okay, so w0 w1 w2 has initially weighted as 0.5. Let's say this is 2, this is 2. So randomly weighted weight vector gave this decision boundary. So we have some um, we have some wrong prediction here, that will be minus in the upper side of this decision boundary. So whenever we get a wrong prediction for misclassified input, we have w transpose x is greater than 0. We want to decrease it based on the input vector, so that w transpose x is less than 0 for this misclassified input. This misclassified input was actually minus, and we classified as predicted as plus. And whenever we have misclassified input actually positive and we have predicted it as negative, so we can, sorry, we will, uh, this is our initial, so this is wrong, so we predicted wrong, so we want to increase w such that w transpose x will be greater than equals to 0. So whenever we misclassify negative input, we want to decrease the w, and whenever we misclassify a positive, we want to increase the w to include that positive one in our decision boundary. Okay, so what we have learned here is that let's say this is our uh, initial weight that we have just randomly given. We want to add something and make this is our new weight vector, so that all the misclassified inputs get classified correctly. So where delta wi, that is the difference that we are adding, is minus va if actual the input was minus and we have predicted plus, and where wi will be plus where actually we have a positive but we predicted negative, so we want to then decrease it. Whenever our actual is negative and we wrong predicted it, so we want to decrease the w to get it right, and whenever we have positive data but we have predicted wrong with, so we want to increase it so that we can include in the decision boundary. So this is the final outcome after summing up all this. So we get wi new, that will be equals to w old, and some difference of the actual minus predicted. This is actual, this is predicted, multiplied with the input data, and here there will be some constant. This constant, it is called learning rate. The rate at which we are learning how to change w, that is called learning rate. Up to this point, I think everything is clear. We will now discuss about OR gate, NAND gate and other gates based on this perceptron